I'd like to continue the discussion on the determination of average reservoir pressure. And this time I would be continuing with or starting with the Rami and Kob method. So Rami and Kob proposed that the average reservoir pressure in the drainage area can be read directly from the Horner semi-log straight line. And this implies that to use the Rami and Kob method, the Horner plot needs to have been produced. So three things are essential to using the Rami and Kob method. The shape of the well drainage area must be known. Is it a circular drainage area? Is it square? Is it hexagonal? Two, where is the well located in the drainage area? Is it central? Is it closer to one of the boundaries? And three, what is the size of the drainage area? The reservoir extent needs to be known to use the Rami and Kob method. So as it was for the Mdh method, the dimensionless producing time will need to be calculated. Now, so knowing the shape of the drainage area and well location, the dimensionless time to reach to the steady state is given in table D1, in the fifth column of table D1. So, knowing the shape of the drainage area and the well location, one is to determine the dimensionless time required to reach to the steady state, as given in the fifth column of table D1. And I would like us to take, so this is table D1. So table D1 is table showing shape factors for various single well drainage areas. These are the conventional, that is regular drainage areas. This is a well centrally placed in a circular drainage area in hexagon. And then you see that these are well placements that are more skewed, but the fifth column here, this is the dimensionless time to reach steady state given in the fifth column here. So the essence of determining the dimensionless time to the steady state from table B is to compare that value to the dimensionless producing time you calculate from your own data. A comparison of the two values, that's the dimensional producing time and dimensionless time to reach the steady state, can result in two scenarios. One, if your dimensionless producing time is less than time to reach to the steady state, this relationship is used. However, if your producing time is greater than the time to pseudo steady state, this relationship involving the shape factor is used. So let's go ahead and see this in using our example. Okay. So this particular example is to demonstrate the use of Ramikorps method. So for the Ramikorps method, you need to produce the Horner plot. You need to extrapolate it to Horner time is 1. You need to read off the slope. And then the next thing would be to calculate your dimensionless producing time. TP is the producing time is given in the question. And all these are provided. Remember that this had been calculated under the Mdh method. This get the producing time. You read off the time to the steady state from the 5th column of table D1. If you compare, of course, 0.01175 is greater than 0.1. Therefore, the second relationship is used, the one that involves the shape factor. And all you need to do is substitute the values. This is your force pressure, 3365. It's the same thing for Mdh and the Rami and Kob method. M is the slope of the Horner plot. This is the shape factor for a circular drainage area with the well centrally placed, and this is your producing time, and this gives 3342. This will be different if your producing time did not get to pseudo steady state, and in that case, you will need to use this relationship, or otherwise use the second relationship. That said, let's go to the Mdh method, and this would build on the Mdh I discussed briefly in the last lecture. So to use the Mdh method to estimate average reservoir drainage and reservoir pressure, either for a circular or square system, you will need to produce the Mdh plot. You produce the Mdh plot, and then, of course, locate the straight line portion. Then on the straight line, you will need to choose any convenient, you choose a point, and of course, for that point, a convenient, the shorting time and the corresponding bottom hole pressure. And then you will now calculate the corresponding dimensionless shorting time for that shorting for the shorting time you selected, and then you would enter with the dimensionless time and read off the dimensionless Mdh pressure from the chart that's figure B5, which I'll show shortly, and then using this relationship, which involves, so for the Mdh method, you do not use the force pressure directly, even though it still comes in somewhere in the equation. Now, instead of the charts, you could use this polynomial, which has been fitted to a curve fitted to this polynomial. You see, this is the dimensionless Mdh pressure as a function of your dimensionless shorting time, and then the constants are used as a function of the geometry. The solid line here stands for closed boundary, while the dotted lines here refers to a constant pressure boundary. This is the plot, of course, for which I showed you the fitted polynomial. The solid line here, this is no flow boundary, which is as in the case of our example, and these are constant for constant pressure boundaries. So here you have dimensionless Mdh pressure. This is shorting time. Now, so this is the Mdh plot. This is obtained from Ahmed and McKinney, Advanced Reservoir Pressure, Advanced Reservoir Engineering, rather. Now, this is the same Mdh plot using the data in the example problem we've been treating. So for the Mdh plot, you have your shorting pressure on the y-axis, and then you have the shorting time on the x-axis. No transformation is done, no reversal of axis. You just plot directly onto the Sumilog graph sheet. So you'll see in this case, obtaining the P1 hour is straightforward. All you do, you just enter 1 hour, you read off the corresponding pressure to get the slope of the straight line portion. Of course, no, first of all, you need to, so this is the portion distorted by Wellbore effects. Here, boundary effects are beginning to set in. So this is the straight line portion of the graph. And then you get the straight line through it. And from there, you could get what the, so you obtain the slope from any of the cycles. So here, and if you look at it, this is about 3344, this is about 3304, and then that gives you 40 psi per log cycle. Here, of course, the red portion here, I just put a series here so that I got the equation of the graph. And of course, these are things you can do in Excel. So one other thing I needed to mention is getting the permeability and skin is the same way, or same formulas we'll have used if it was the Mdh, but the difference is note you're plotting your shorting pressures against shorting time. So to solve the problem, I have chosen a convenient time of 2 hours. So here, shorting time, and then the corresponding pressure is 3277.5. I was able to get the 0.5 because I used the trend line. And of course, the next thing is to get the dimensionless shorting time. So all you need to substitute, this is 2 hours, this is 12.8, this is pi 2640 square, 22.5 times 10 square minus 6, 0.2, 0.09, substitute that, you would get this. So you use this, and then you enter these plots, and if you trace it down, you will get about 1.9. So it's something like this. I think it's somewhere here. I'll give my line something, and then you read off this one. So that gives you about 1.9. So once that is obtained, the 1.9 you get, that's the dimensionless Mdh pressure, is substituted here. So this is the shorting pressure you picked arbitrarily. M, that's the slope of the graph. This is the dimensionless pressure and substituted. So here we get 3343.5, which is close to what we got from the other two methods. For the Dietz method relies on the Mdh plot. So it says that indicated that if the test well has been producing long enough to reach the steady state before shorting, the average pressure can be read directly from the Mdh semi-log straight line. So to use the Dietz method, you need to have produced the Mdh straight line, get the slope, and then you can now calculate. So if you take a look at the equation here, this is given, you'll be given this, all this from there, and then this is the shape factor that corresponds to your own drainage area. This is permeability obtained from the slope M. So the method assumes that the well has flowed sufficiently until the steady state is reached. Of course, you know that is the assumption on which the Mdh method is based. Usually, it's preferred for wells with very little damage. I think somewhere between scale of 3 and -3. And then this is the procedure. So for your own given reservoir shape and well location, you read the shape factor from table D1 and then calculate the Dietz shortening time, and then you would, of course, you need to prepare the Mdh plot. And then you enter the Mdh plot with the Dietz shortening time to get the corresponding average reservoir pressure on the semi-log straight line. So this demonstrates what mentioned here. So based on the Mdh plots, which I showed previously, M was 40, the P1 hour 3266, and then you can't obtain the force pressure directly because you are not, there's no Horner's time of 1. So this equation is used to obtain the force pressure. That's if you're interested in that, even though it doesn't come up in your final equation. So the shortening time based on this equation, if you substitute, gives you 83.5 hours. Your test duration didn't extend up to 83.5 hours. So this equation is used. The average pressure is equal to P1 hour plus M times the log of shortening time. And this is the shortening time obtained from here. So P1 hour this is read from the Mdh plot. This is the slope of the Mdh plot, and this is obtained from step 3, and this gives 3343. See that this is still close to the pressures we've obtained. Now, Arari presented a simple method for calculating average reservoir pressure without the use of graphs. So he presented equations for no-flow boundary reservoirs and for constant boundary reservoirs. These equations are actually the same thing. If you look at it, this is written in terms of reservoir extent, while this is in terms of drainage area, and the same thing here. So, but if you are going to consider, of course, different well positions and reservoir diametries, the Dietz shape factor needs to be incorporated, and that's what you have in the 2 equations below. So this corresponds to this second equation here, and this for the fourth equation. So the direct method is quite simple. All you need to do is to substitute. So using the first equation here, PWF, this is the last flowing pressure before the well was shortened. It's obtained from the first column of the example, and then you have this is the flowing the rate at which the well was flowing. This is viscosity, formation volume factor, permeability as obtained, the thickness 2, and this is reservoir extent, and then so by substitution, this gives us 3349.77 psi, and you see that without the use of graphs, one gets something which is quite close. I think this is a little higher, but still close to what we've obtained. Now, let me speak briefly about the Muskat, the modified Muskat method. Unlike the others, this one is a trial and error method, and it is preferred for constant pressure systems, of course, like water injection systems, where constant pressure is maintained to a large extent. The reason is because the assumption is that this linear relationship holds. The log of the difference between the average reservoir pressure and the shorting bottom hole pressure is proportional to your shorting time. And constant pressure systems it's easier to identify the straight line for constant pressure systems than for wells producing under steady states. Let me mention that the modified Muskat method is for late time data, recommended to be used on late time data. Late time data are data for which when you have pseudo-steady state well developed, not at the onset of pseudo-steady state, but when pseudo-steady state is well developed. And it's been found to be valid within this range. I will demonstrate that. So the one advantage of using the Mdh method is that it can be applied to hydraulically fractured wells and layered reservoirs for which the Mdh method is not applicable. However, it's limited to reservoir drainage areas for which you have the wells at the center. And more so, of course, it requires that the well has been flown well beyond pseudo steady state. So this diagram here shows how it is used. Now, P bar is assumed, and then based on that assumed value, this what you have on the I think this the ordinate is reduced for each shorting time. The correct assumed pressure should yield a straight line. Of course, if your pressure is exaggerated or at least way above, it will come up, and then this is for an underestimated pressure. Now, so for the purpose of this class, I won't discuss these next two slides, but this, as we've done for the other methods, let's see how the Muskat is used and whether it's applicable for our case. So one of the things you could do is to check whether the Muskat method is valid for your own test data. So what was done here was simply to substitute is the porosity in our question, viscosity, compressibility factor, the reservoir extent, permeability, and this gives a lower bound of 55.4 hours. Unfortunately, our test duration is 37.5 hours, which is less than our lower limit. So it's unlikely that this method will be applicable. But if you still go ahead to use it, you're most likely going to come up with something like this. That's this picture which is sent in the background. So what I did was to assume this is 3340, 3345, 3350, and then you see, unfortunately, which is not unfortunate, but in this case, by the time you get to about 35 hours of shorting, all three plots begin to flatten out. And probably this just tells us that this is not the range of values for which it's valid to use the Muskat method. Now, finally, I would like to state that even though average reservoir pressure is primarily determined from pressure build-up tests, in 2010, Agua presented an expression through which you can obtain average reservoir pressure from drawdown tests. And it's a very simple expression. The average reservoir pressure is equal to the flowing pressure plus the ratio of 887.18 times flowing rate from transformation volume factor times the viscosity divided by the permeability thickness product. Now, this equation doesn't consider the Dietz shape factor, but it stipulates that the conditions, the condition that the well has been flowing into steady state, similar to the modified Muskat method, is very important. And I think in this lecture I've mentioned late steady state. I think our next two classes I'll begin to shed some light on the late steady state, where we build on some different plots. That's the log plot, of course, which helps us, which is more powerful than the semi-log plot, and that will bring our discussion on well testing methods to a head. Thank you very much.